Hello, my name is Hameem Gorabi, and today I'll be presenting my presentation on introductory wind turbine aerodynamics based on a literature review that I wrote for this class. Humans have been using wind power for an incredibly long time, well beyond written history. Archaeological evidence suggests that we've been doing it for more than 40 millennium, and windmills utilizing wind power have been used for centuries. In a more recent history, the first electrical wind turbines were essentially adapted windmills on low efficiency DC grids. These had a limited use case and a limited range. Mounting fuel shortages during the World Wars led to a growing interest in alternative fuel sources like wind. And our modern knowledge of the critical flaws with fossil fuels, like geopolitical supply issues and oncoming scarcity, uh, also advanced the interest in alternative energy like wind turbines. Turbine overview. Wind turbines can be driven by drag or lift. Lift is more efficient, so most turbines are driven by lift. And because they're lift driven, they have some similarities with aircraft airfoils, uh, though they are a bit different due to being optimized for turbines. Horizontal axis wind turbines, which are pictured in the bottom picture, I'm sure you've seen, they're very common. Vertical axis wind turbines are a bit less common, but they have several potential uses and several key advantages which facilitate those uses. The power available to a wind turbine uh, is based on the incoming flow of air. So the kinetic energy of that flow and the mass flow of that air. And those two things we can derive the sort of maximum power of the incoming air. And from that derivation, which we have on the slide here, we find that our area and our density scale our power linearly, but our incoming velocity scales cubically our maximum power. So the incoming velocity depends on the site, and thus our site selection is extremely important when it comes to wind turbines. Let's consider the case of an ideal horizontal axis turbine and just one of the blades. Now let's take a slice of that blade and consider the 2D flow around it. Now, Prandtl established that we can take this local data and apply it as long as we adjust for angle of attack along the entire spanwise length of a long slender wing, so that we're going to do just that. That reaction force F shown on the previous slide can be decomposed into lift and drag. Our lift is driving the system. We have it characterized there. And from that and some applied dynamics to a uniform rotation, we can figure out the power and then relate that to our previous available power as a coefficient of power, or the converted power, which is our aerodynamic efficiency under ideal conditions. Betz proved that the coefficient cannot be greater than 0.593 under completely ideal conditions. Modern systems reach a coefficient of roughly 0.5 and they're considered very efficient. Vertical axis wind turbines apply similar principles but very differently. In our case, it's the tangential speed of these blades that matters, that's driving the system, and that is mostly contributed to by lift, but can also be contributed to a little bit by drag, but we still consider it to be lift driven. We have that tangential force expressed as a function of the lift and drag there. And then that's evaluated across a revolution, and then we find through a little bit of basic dynamics the power provided per blade, and then we make a similar relation as we did for the horizontal axis wind turbines with our new vertical information, which ultimately becomes a function of the free stream velocity and our tip speed, which then is described as our tip speed ratio, lambda, which is used extensively when evaluating the turbines in research. So horizontal axis wind turbines have an established most efficient configuration theoretically. Vertical axis turbines do not. So the most optimal design is still up in the air, still being developed. Uh, but even though they do not reach that same level of efficiency and have not been optimized to the maximum, there are still several key advantages that make vertical axis wind turbines very competitive. Torque ripple is a phenomenon that occurs when there's variation of instantaneous torque along the rotation of a turbine. It's caused by a variety of things, but in horizontal axis wind turbines, it's mostly drag, and vertical axis wind turbines is mostly the intrinsic variation of the angle of attack. There are a few common base designs of vertical axis wind turbines, and they each have aerodynamic advantages and disadvantages. Those three are shown below as A, B, and C, the Musgrove, Darius, and Gorlov turbines. The Musgrove straight-bladed turbines have the highest theoretical efficiency and good starting characteristics with simple geometry, though they require sturdy support struts. The Darius curved blade turbines do not require support struts, though they can still have them as shown in the picture. And they have reduced efficiency towards the top and the bottom, which means you need a really long uh, turbine to get a decent efficiency, which also means a long unsupported shaft, which you need guy cables, also shown in the picture, to keep upright. And the curvature also means more challenging self-regulation in regards to stalling. Gorlov helical bladed turbines offset torque ripple, which is their key advantage. They also have better starting characteristics than straight-bladed turbines, but they do have a reduced efficiency due to their helical sweep, and their geometry does introduce more challenging stall regulation characteristics. So in summary, the power accessible to a wind turbine is cubically dependent on the free stream velocity and linearly dependent on the area supplied that it covers. And wind turbines use airfoil blades, which are generally lift driven due to efficiency gains. Horizontal axis wind turbines have relatively high aerodynamic efficiency and are considered optimized. Vertical axis, not optimized, and we have less overall efficiency, but we have a bunch of desirable characteristics that horizontals don't have. Torque ripple negatively affects fatigue life, power quality, and shaft pullout, so it's something we need to consider and avoid. And there are three variations commonly of vertical axis wind turbines, each with their relative advantages and disadvantages. And that's all. Thank you.